Now we're going to see if the spherical harmonics obey the condition of orthonormality. So we said that for Hermitian operators, all of the eigenfunctions which have different energy eigenvalues have to be orthogonal to each other, meaning that the integral of psi star psi over the entire domain of the function has to be equal to either 1 if all the quantum numbers are the same and 0 if they are different. So for our spherical harmonics, we have the y L of m or y j of m of theta and phi. Some people say L, some people say j. It's the same thing. Is our wave function, which is a function of theta and phi in spherical polar coordinates. And that can be separated into a function of theta and a function of phi. And you get some normalization constant here depending on j and m, 2j plus 1 over 4 pi, j minus absolute value of m factorial over j plus absolute value of m factorial, all of that in a square root, times an associated Legendre function, which depends on j and the absolute value of m, and the variable in that Legendre polynomial is cosine of theta. And then there's a complex exponential at the end. So you can look up the associated Legendre function to see what its value is for a given j and m, plug in cosine where it has x, and our complex exponential e of I m phi, which we know complex exponentials can be expressed as just sines and cosines in the real and imaginary planes. And this quantum number j is some integer, starts at 0, goes up from there. And within a given value of j, m can take on all values of integers which are between minus j and plus j. So for j equals 0, it can be 0. For j equals 1, it can be minus 1, 0, and 1. For j equals 2, it can be minus 2, minus 1, 0, 1, and 2, etc. This is where the degeneracy in the rigid rotator comes from, in that there are two j plus 1 states for a given value of j, because there are two j plus 1 values of m for a given value of j. But on to this orthonormality condition. So first thing we can look at is, let's look at the integral from minus 1 to 1 of a Legendre polynomial, p of j, times another Legendre polynomial, p of j prime. Both of these depending on x. Integrate them with respect to x. In our Dirac notation, we would refer to this as a bra of j and a ket of j prime for the total bracket. And this is a special property of Legendre polynomials, that this equals the Kronecker delta function j of j times j prime. And let's just remind ourselves that the Kronecker delta for two integers m and n would be 1 if m equals n and 0 if m not equal to n. So again, that's called the Kronecker delta, that symbol there, depending on two numbers m and n. Okay, so that's nice, but how does that relate to what we've got here? Well, this integral that we've got up here, if we just continue that down here, that is also equal to the integral of 0 to pi for p of j when you put in cosine theta and pj prime cosine of theta, because the cosine of pi is 1, the cosine of 0 is minus 1, so putting in cosine theta is the same as integrating x from minus 1 to 1 is the same as integrating cosine from 0 to pi. And then that times sine theta d theta, which is the volume element for a polar angle in spherical polar coordinates. It's not just dx, dy, dz like it is in Cartesian. The volume element in spherical polar is r squared sine theta dr d theta d phi. So this sine phi comes from the different volume element when we go to spherical polar coordinates. But this integral as well is also going to come out to be a Kronecker delta, which is 2 delta j j prime over 2j plus 1. And whenever we have this function here, we see that this part of the normalization here, where we have this 2j plus 1 on top and a 2 which is going to be on the bottom here, that part of the normalization comes from this fact that this integration of the Legendre functions, the associated Legendre function over this interval of theta, gives us this factor here. So this implies to us that the set of these functions of theta, which are going to depend on j and the value of the absolute magnitude of m, the set of all of those are orthonormal. Because we can pick some normalization constant for all of them, which is going to make them equal to 1 if j equals j prime, and we see they're going to equal 0 if j doesn't equal j prime, because this Kronecker delta will give us a 0. So the theta part is orthonormal to itself. Check, that is a good thing. And then looking also at phi, the integral from 0 to 2 pi, that's the whole range of phi, of d phi star of phi times phi. So that's complex conjugate of the phi part of the wave function times itself. This integral over the entire range of phi should give us 1 or 0. And in Dirac notation, this would be the bracket m prime n, if we say it depends on m prime here and m there. Then continuing this integral on to the next line, we're going to have integral 0 to 2 pi d phi. Phi of phi is going to be e to the minus I m prime phi. Taking the complex conjugate moves us from positive I to minus I, because that's what complex conjugate means. We switch any minus signs on the imaginary part, times e to the plus I m times phi, and this equals, continuing on to the next line, the integral of 0 to 2 pi d phi of e to the minus I m prime minus m phi. And this is going to equal, if m prime equals m, then this is e to the 0, which is 1. Integrating from 0 to 2 pi gives us just 2 pi. If m is not equal to m prime, then we get a function which oscillates and has equal parts above and below 0, going from 0 to 2 pi, and you can convince yourself that the full integral would be 0 if they're not equal. So this would give us 2 pi times m delta m prime. So the integral is 2 pi if they're equal, and it is 0 if they are not equal. And so this means that the set of phi of m of phi are also orthonormal to each other. They are normalized, meaning we get this extra factor of square root 1 over 2 pi from this 2 pi here. So we can choose a normalization constant, which makes it normal. And they're orthogonal because they equal 0 if m and m prime aren't the same. Okay, so for our total wave function, which is theta of theta times phi of phi, we're going to get a total integral which looks like this, which is the integral from 0 to 2 pi d phi, integral of 0 to pi sine theta d theta, that's the total volume element there on a unit sphere, of psi star jm, if I want to use this type of notation here, theta and phi are my variables, times psi of jm theta and phi, say j prime and m prime, a different value of j and m. And this would be equal to, under our notation, a Dirac bracket, which is j prime, m prime, j, m, which is going to be delta j prime, delta m prime. The theta part is orthonormal to itself, so you get a Kronecker delta there. The phi part is orthonormal to itself, you get a Kronecker delta there. So that means that our total wave function, want to pick this cyan here, our total wave function, the spherical harmonics y L of m, y j of m, psi of theta phi, whatever you want to call them, that they are indeed orthonormal. And this is how orthonormality is going to work in general for most quantum systems that we see. If you have a certain number of dimensions, in this case we have 2 dimensions, in that case we're going to get 2 distinct quantum numbers, j and m, and we have a wave function in each spatial coordinate, the one in theta and one in phi, and within each coordinate of the wave function in that coordinate is orthonormal to itself, and a product of things which are orthonormal gives us something which is completely orthonormal. So if you have a spherical harmonic and j and m are not both the same, that will give you an integral like this, will give you 0, and if they are both the same, that integral will give you a value of 1.